So we begin with section 6 of L&L's classical mechanics. Landau titles this section energy. So during the motion of a mechanical system, the two S quantities qi and q dot I, which specify the state of the system and vary with time, and there do exist, however, functions of these quantities whose values remain constant during the motion, and these depend only on the initial conditions. Such functions are called integrals of the motion. Now, the number of independent integrals of the motion for a closed system with s degrees of freedom is 2s minus 1. This is evident from the following simple arguments. The general solution of the equations of motion contain 2s arbitrary constants. Since the equations of motion for a closed system do not involve the time explicitly, the choice of the origin of time is entirely arbitrary, and one of the arbitrary constants in the solution of the equations can always be taken as an additive constant t naught in the time. So if we use t plus t naught to find our arbitrary constants, this would be equivalent of saying t plus 0, which is just t, a different arbitrary constant. So our 2s quantities that are arbitrary constants that we have for each equation of motion thus becomes 2s minus 1 because of our arbitrary choice of origin of time. Now, not all integrals of the motion, however, are of equal importance in mechanics. There are some whose consistency is of profound significance, deriving from the fundamental homogeneity and isotropy of time and space. The quantities represented by such integrals of the motion are said to be conserved, and they have an important property of being additive. Their values for a system composed of several parts whose interaction is negligible are equal to the sums of their values for the individual parts. This is basically saying if we have a system with energy 1 and a different system with energy 2, and we see these systems interact, we would thus have a total energy for the system. It is to this additivity that the quantities conserved owe their special importance in mechanics. Let's suppose, for example, that two bodies interact during a certain interval of time, and since each of the additive integrals of the whole system is both before and after the interaction equal to the sum of its values for the two bodies separately, the conservation laws for these quantities immediately make possible various conclusions regarding the state of the bodies after the interaction. Now, Landau basically proves this by using the homogeneity of time. So, if we take the time derivative of our Lagrangian, this would just be equal to del L del Q Q dot minus del L del Q dot Q double dot plus some function of our Lagrangian plus the partial derivative of some function with our Lagrangian respect to time. Now, we know from Euler's formula, which is del L del Q is equal to minus del L del Q dot ddt. And, sorry, not minus, it's equal to, because they're minus when they're equal to 0. So if we replace this term in our time derivative equation, ddt of L is equal to del L del Q dot, I should probably write ddt first, ddt del L del Q dot minus del L del Q dot Q double dot plus del L del T. Now, from here, if we rearrange, we can get d dt of del L del q dot minus del L del q double dot minus d dt of L plus del L del t is equal to 0. And if we isolate our terms with a ddt, we can just simply move the del L del t to the other side, equal to minus del L del t. If we notice here, we have a product rule. So this is the derivative of a product. It's the derivative of a first term times the derivative of the second. So we can simply write this as d dt of del L del q dot minus d dt of L equals minus del L del t. And we can also factor out the d dt. And simply state it as such. Now, our Lagrangian does not depend explicitly on time. So, since it doesn't depend explicitly on time, this term now becomes 0. So we have d dt of del L del q dot minus L is equal to 0. And we know from basic mathematics that if you have the time derivative of a function and it's equal to 0, that function is constant in time. So if we denote this as the energy of the system, we can say that that's what it's called. And we know and can prove this by using Euler's theorem for homogeneous functions. So Euler's theorem for homogeneous functions states that if you have a function of degree n, which is homogeneous in its variables, it is equal to the sum of that variable times the partial derivative of that variable, which is also equal to the degree of that function times the function. So applying this to our kinetic energy, since our kinetic energy is a quadratic function because it's 1/2 m q dot squared, that would mean that it is of degree 2. So we can actually write this term del L del q dot, and we notice it is of similar form as Euler's theorem for homogeneous functions. So the only function in our Lagrangian that is dependent on q dot is going to be t. So we have del t del q dot, and it's a quadratic of degree 2. So that would just make it equal to 2t. And from there, if we do 2t minus L, we would just get that is equal to the energy. And proving this, we can use 2t minus t minus u, the definition for our Lagrangian. We would just get that the energy is equal to t plus u.